Hello there, and welcome back to Sleeping with Science Stories. Find the most comfortable position for yourself. You may be lying in bed, resting your head on a soft pillow. You may be sitting back, letting your body be fully supported. Tonight, we will not stay on Earth. We will gently travel through the solar system, visiting the silent companions of the planets, the moons. If this is your first time visiting the channel, remember to subscribe so you don't miss the journeys ahead. And if this video helps you relax, leave a gentle like as a quiet thank you. Moons. Small worlds orbiting larger worlds. Natural satellites that have existed for billions of years, shaping tides, stabilizing climates, and carrying the history of the solar system. Some moons lie dormant, cold, and silent, their surfaces covered with the scars of time. Others are alive, with volcanic fire erupting hundreds of kilometers high. Some hide vast oceans beneath thick layers of ice where life may exist. From our familiar moon, the ancient companion that has been with us for more than 4 billion years, slowly drifting away from us each year. Every night of a full moon, you look up at the sky and see that gentle silver light. It seems eternal, unchanging, always there. But the truth is that the moon is gradually moving away from us. Each year, the moon moves about 3.8 centimeters away from Earth, roughly the rate at which your fingernails grow. That number sounds small, insignificant. But over millions, billions of years, it adds up. In the distant past, the moon was much closer to Earth. It appeared larger in the sky, perhaps twice the size we see today. And this drifting away has consequences. The moon and Earth are connected by gravity and tidal forces. As the moon moves away, it pulls rotational energy from Earth, slowing the rotation of our planet. This means that the length of a day on Earth is gradually increasing. When the moon first formed, about 5 billion years ago, a day on Earth lasted only about 5 hours. Earth was spinning extremely fast. The moon was very close, filling nearly the entire sky. Over billions of years, the moon moved farther away. Earth slowed down, and the days grew longer. During the time of the dinosaurs, about 100 million years ago, a day lasted about 23 hours. Today, it is 24 hours, and this process continues. In the distant future, billions of years from now, a day on Earth may last 47 hours, and the moon will be much farther away, moving more slowly across the sky. But the moon is not just a cold, lifeless rock as we often think. It has a rich and surprising history. Billions of years ago, the moon once had a thin atmosphere. This may sound impossible. The moon is small, its gravity weak. How could it hold an atmosphere? But scientists believe that for a short period, around 3 to 4 billion years ago, intense volcanic activity on the moon released enough gases to form a temporary atmosphere. This atmosphere was very thin compared to Earth's, and it did not last long, perhaps only tens of millions of years, before dissipating into space. But during that time, the moon may have had atmospheric pressure 2 to 3 times greater than that of Mars today. And this temporary atmosphere may have helped retain small amounts of liquid water on the surface, at least in some protected areas. Speaking of water, the moon is not completely dry, as we once thought. At the lunar poles, in deep craters that lie in permanent darkness, places where sunlight never reaches, there is water, ice. These craters are positioned at angles such that their rims always block sunlight. Temperatures at the bottom of these craters are extremely cold, down to minus 230 degrees Celsius. Cold enough that water never evaporates, even in a vacuum. Over billions of years, water from comet impacts and from the solar wind interacting with rocks has accumulated in these craters. Today, there may be billions of tons of water ice hidden in these permanently shadowed regions. This is an important discovery for the future. If humans want to build bases on the moon, this water could be a valuable resource for drinking, for producing oxygen, and for making rocket fuel. And if we look back in time, the moon was once very different from what it is today. When the moon was young, its surface was a vast ocean of lava. The entire moon glowed red hot with molten rock. It was bright enough to be seen from Earth as a giant red sphere in the sky. Gradually, the moon cooled. The crust solidified. But beneath the surface, magma remained hot. And between 3 and 4 billion years ago, massive meteorites and asteroids collided with the moon, creating enormous impact craters. These impacts shattered the crust, allowing magma from below to flow out. Lava spread and filled the large impact basins, forming dark, flat seas. These dark regions, called maria, from the Latin word for seas, are what we see when we look at the moon at night. They are not water. They are basalt volcanic rock that cooled and hardened billions of years ago. The brighter regions surrounding these seas are older highlands, less affected by later lava flows. And if you ever thought the moon was completely still, without geological activity, think again. The moon has moonquakes. These vibrations are not as strong as earthquakes on Earth, but they occur frequently. There are 4 types of moonquakes: deep quakes, thermal quakes, impact quakes, and shallow quakes. The most notable are shallow moonquakes. They occur near the surface and can reach a magnitude of 5.5 on the Richter scale, enough to damage structures if there were human bases there. And there is something strange about moonquakes. They last extremely long. On Earth, an earthquake usually lasts a few seconds or minutes. But moonquakes can shake for more than 10 minutes, and the reverberations can continue for hours. Why? Because the moon is dry and cold. On Earth, water within rocks helps absorb and dampen seismic waves. But on the moon, the rocks are dry and rigid, allowing seismic waves to travel farther and longer, like a bell ringing for a long time after being struck. And when Apollo astronauts set foot on the moon, they discovered another strange thing: lunar dust. Regolith, the dust and fragmented rock covering the moon's surface, is very different from dust on Earth. Because there is no wind or water to erode and round the particles, lunar dust retains sharp edges like broken glass. These tiny edges can cut through astronauts' gloves and clothing. And this dust is extremely sticky. It clings to everything: spacesuits, equipment, inside spacecraft. Apollo astronauts reported that they could not completely remove lunar dust. It sticks because the particles carry electrostatic charges from solar radiation. And there is another strange detail. Lunar dust has a smell. Astronauts described it as similar to the smell of spent gunpowder or wet charcoal. No one knows exactly why, but it may be due to chemical reactions occurring when lunar dust comes into contact with the moist air inside the spacecraft. But perhaps the most important role of the moon is not what it is, but what it does for Earth. The moon stabilizes Earth's axis of rotation. Earth rotates around an axis tilted about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt creates the seasons. But without the moon, this axis would wobble significantly over time due to gravitational forces from the Sun and other planets. Mars, which does not have a large moon to stabilize it, has an axial tilt that varies from 0 degrees to 60 degrees over millions of years. This creates extreme climate changes. Sometimes the poles receive direct sunlight. Sometimes they remain in darkness. But Earth, thanks to the moon, has a stable axis of rotation. Its tilt varies by only about 1 to 2 degrees over thousands of years. This means our climate is relatively stable and predictable. And this climate stability may be a key factor in the evolution of complex life on Earth. If the climate fluctuated drastically, from extreme heat to extreme cold in short cycles, life might not have enough time to adapt and develop. So, in a sense, we owe our existence to the moon, and the origin of the moon is no less extraordinary. The most widely accepted hypothesis is that the moon was born from a catastrophic collision. About 4.5 billion years ago, not long after Earth formed, a Mars-sized planet named Theia collided with Earth. This was not a head-on collision. It was an oblique impact at an angle. Theia struck Earth at tremendous speed, and the energy of the impact melted both bodies. A vast amount of material molten rock, metal, gas was ejected into orbit around Earth. The core of Theia merged with Earth's core, but most of the outer layers of both bodies formed a disk of debris orbiting Earth. Over time, perhaps only a few hundred years, this debris collided and stuck together, gradually forming a single object, the moon. This is why the chemical composition of the moon is very similar to Earth's crust. They were once part of the same material, and this is also why the moon is poor in metals. Compared to Earth, most of the metals sank into Earth's core during the collision. And there is another strange feature of the moon. It always shows the same face to Earth. When you look up at the moon, you always see the same side. The other side, the dark side of the moon, or more accurately, the far side, is never visible from Earth. This happens because the moon is tidally locked. The time it takes the moon to rotate once on its axis is exactly the same as the time it takes to orbit Earth, about 27.3 days. As a result, the same face always points toward Earth. Tidal locking occurs because Earth's gravity acts unevenly on the moon. The side closer to Earth is pulled more strongly than the far side. Over millions of years, this tidal force slowed the moon's rotation until it synchronized with its orbit. And this means that throughout human history, until we sent spacecraft in the 1960s, no one had ever seen the far side of the moon. When the first images of the far side were sent back by the Soviet spacecraft Luna 3 in 1959, scientists were surprised. The far side looks very different from the near side. It has far fewer dark seas and many more impact craters. Its entire surface is rough, heavily scarred, and appears older. Why are the two sides so different? It remains a mystery, but it may be because the crust on the far side is thicker, making it more difficult for magma to erupt to the surface and form the seas. And one final detail about the moon. Its shape is not perfectly spherical. The moon has a slightly egg-like shape, slightly elongated in the direction of Earth. This deformation is very small, only a few kilometers, but it can be measured. It is the result of tidal forces from Earth. When the moon was still molten, this force stretched it into an egg shape. When the moon cooled and solidified, it retained that shape. So the moon, the familiar, silent companion in the night sky, is truly a world full of mysteries. It is slowly moving away from us, slowing Earth's rotation and lengthening our days. It stabilizes our climate, allowing life to develop. It was born from an unimaginable violent collision. It hides ice in permanently dark craters. It trembles with moonquakes that last for hours. And every night, when you look up, you are seeing a world with a 4.5 billion year history. A world that has witnessed the rise of life on Earth, the extinction of the dinosaurs, and the emergence of humans. The moon has been there for all of it, and it will still be there, quietly orbiting, long after we are gone. While Earth's moon is large, round, and familiar, the solar system contains hundreds of other moons, and many of them look as if they do not belong to reality. Some look like potatoes. Some look like ravioli. Some look like flying saucers. Some have shapes so strange that scientists are still trying to understand how they can exist. These small moons tell stories of violent collisions, strange gravity, and cosmic accidents. They are the remaining fragments from the formation of the solar system, silent witnesses to the chaotic history of the planets. Let's begin with one of the most unfortunate moons in the solar system, Phobos. Phobos orbits Mars, along with its smaller twin Deimos. These two moons are named from ancient Greek. Phobos means fear, and Deimos means terror, named after the sons of the war god Ares. Phobos is tiny, only about 22 kilometers across at its widest. It has an irregular shape, like a dented and rough potato. Its surface is covered with scars from meteorite impacts over billions of years. But what makes Phobos special is not its shape or size. It is its fate. Phobos is dying a slow and inevitable death. This moon orbits Mars at an extremely close distance, only about 6,000 kilometers from the planet's surface. That is so close that it orbits Mars faster than Mars rotates. Phobos takes only 7 hours and 39 minutes to complete one orbit around Mars. This means that if you stood on the surface of Mars and looked up at the sky, you would see Phobos rise in the west, move quickly across the sky, and set in the east opposite to the motion of the sun and the stars. And it does this 3 times in a single Martian day. But tidal forces from Mars are pulling Phobos inward. Every century, its orbit decreases by about 2 meters. That number sounds small, but it adds up. Scientists estimate that in about 50 million years, a short time on geological scales, Phobos will come too close to Mars. At that point, tidal forces will become too strong. Phobos will be torn apart into thousands of fragments, forming a beautiful ring around Mars similar to Saturn's rings, but smaller and more temporary. Eventually, over millions of years afterward, these fragments will gradually fall onto the surface of Mars like a prolonged meteor shower. Phobos is living its final days, and we are fortunate to observe it while it is still intact. The surface of Phobos is also strange. It is covered with long, parallel grooves, fractures that run across the surface. These grooves may be the first signs of its coming destruction cracks created by tidal forces that are slowly pulling the moon apart. And there is a massive impact crater on Phobos named Stickney, nearly 10 kilometers wide, almost half the width of the entire moon. The impact that created this crater nearly destroyed Phobos completely. If the meteorite had been slightly larger, or the impact slightly stronger, Phobos might have been torn apart billions of years ago. Now, let's move to a completely different world. One of the strangest moons of Saturn, Pan. Pan is a tiny moon, only about 35 kilometers across, orbiting Saturn within the A ring, one of the main rings of this giant gas planet. And Pan's shape is truly unbelievable. It looks like a cosmic ravioli, or like a flying saucer, or like a walnut. It has a bulging equator, a ridge that runs around the middle of the moon, giving it a flat, disc-like shape. How can a moon have such a shape? The answer lies in its location. Pan moves through the Encke gap, a gap within Saturn's A ring. As Pan moves, it clears ice and rock particles from its path, keeping the gap open. But some particles are still captured by Pan's weak gravity. These particles accumulate around the moon's equator, where centrifugal force from Pan's rotation pushes them outward. Over millions of years, this material builds up, forming the strange equatorial ridge. The result is a moon that looks as if it were assembled from two different parts, a spherical core with a flat disk wrapped around its middle. Pan is not alone in this strange shape. Atlas, another moon of Saturn, has the same ravioli-like shape with an equatorial ridge. The same phenomenon occurs with Pandora and Prometheus, two other small shepherd moons of Saturn. All of these moons orbit within or near the rings, and all accumulate material from the rings around their equators, creating shapes unlike anything else in the solar system. And if you think Pan is strange, meet Hyperion. Hyperion is a moon of Saturn with such an irregular shape that it looks like a giant sponge or a half-eaten potato. It is about 360 kilometers across at its longest dimension, but it has no regular shape. It is lumpy, rough, and full of craters. But what is truly strange about Hyperion is not its shape. It is the way it rotates. Most moons and planets rotate in a predictable way. They have a stable axis and spin at a steady rate, but not Hyperion. Hyperion rotates chaotically. Its axis orientation changes unpredictably. Its rotation speed varies. It tumbles, spins, and flips through space in seemingly random ways. This happens because Hyperion has an irregular shape and an eccentric orbit. Gravitational forces from Saturn and the large moon Titan pull and tug on Hyperion in different directions. Because Hyperion is not symmetrical, these forces do not balance, causing the moon to rotate chaotically. If you stood on the surface of Hyperion, you would never know which direction is up or when day would end. Saturn would move across the sky, along unpredictable paths. The sun might rise and set multiple times at random intervals. Hyperion is one of the largest chaotically rotating objects known in the solar system. Hyperion's surface is also strange. It is covered with deep craters that have hexagonal or other unusual shapes. These craters are not just ordinary impact craters. They appear to have been shaped by a different process. Scientists think that Hyperion has an extremely low density. It is like a giant sponge, with a lot of empty space inside. When meteoroids strike, instead of creating typical round craters, the impact energy spreads through the porous structure, producing these unusual shapes. And now, let's talk about one of the most famous-looking moons in popular culture, Mimas. Mimas is a moon of Saturn, about 400 kilometers in diameter. It looks fairly ordinary, except for one detail, a Wishal impact crater called Herschel, 130 kilometers wide. This crater is so large that, from a certain angle, Mimas looks exactly like the Death Star from Star Wars, a gray sphere with a large, dark circle on one side. The resemblance is purely coincidental. Star Wars was released in 1977, but detailed images of Mimas were not captured until 1980 by the Voyager 1 spacecraft. But the coincidence has made Mimas famous. The impact that created the Herschel crater likely nearly destroyed Mimas. The crater is about 10 kilometers deep, with a central peak rising 6 kilometers much taller, relative to its size, than the highest mountain on Earth. On the opposite side of Mimas from the Herschel crater, the surface shows fractures and deformations, possibly shock waves from the impact traveling through the entire moon and producing effects on the far side. But Mimas has a recently discovered secret. In recent years, scientists analyzing Mimas's orbit detected small anomalies, subtle oscillations in the way it moves. These oscillations suggest that the interior of Mimas may not be as uniform as it appears. In 2024, research concluded that Mimas may have a hidden liquid water ocean deep beneath its thick, icy crust. This was a major surprise. The surface of Mimas looks ancient, heavily scarred, with no signs of geological activity. It does not resemble Europa with its fractured surface, or Enceladus venting water into space. It looks dead. But beneath the thick crust, there may be a warm ocean, heated by tidal forces from Saturn. If true, Mimas would join the growing list of moons that may contain subsurface oceans, a list that continues to expand. Mimas would be a disguised moon dead on the outside, but potentially harboring life within. All of these strange small moons, Phobos falling toward its death, Pan shaped like a ravioli, Hyperion tumbling chaotically, Mimas resembling the Death Star, with a hidden ocean share, one thing in common: they show us that gravity and collisions can create unimaginable shapes and destinies. Most of these small moons originate from three processes. Some are debris from giant impacts. When two large bodies collided in the distant past, the ejected fragments could reassemble into small moons. Their irregular shapes are traces of that violent origin. Some are captured asteroids or comets, cosmic wanderers that came too close to a planet and were trapped by its gravity. These moons often have unusual, tilted, or even retrograde orbits relative to the planet's rotation. and some are survivors from the formation of the solar system, primitive material that never accumulated enough mass to become planets, but large enough to persist as small moons. Each strange small moon is a piece of history. They tell stories of ancient collisions, of gravity sculpting shapes over billions of years, of chaos and chance in the formation of the solar system. And they remind us that the universe has a richer imagination than we do. It creates forms we never expect, orbits we cannot predict, worlds that challenge our definitions of what is possible and impossible. And know that out there, in the darkness of the solar system, these strange little worlds are quietly spinning, each with its own story, each a small wonder of nature. When we think about where to search for life beyond Earth, we often think of planets. But perhaps we are looking in the wrong place. Some of the most promising places for life in the solar system are not planets. They are moons. And not on their surfaces, but deep beneath tens of kilometers of ice. Hidden beneath these cold, icy shells are vast, dark oceans that may contain more water than all the oceans on Earth combined. And these oceans have energy, suitable temperatures, and the necessary chemicals, all the basic ingredients for life as we know it. Let's begin with one of the top candidates, Europa. Europa is one of the 4 large moons of Jupiter. The Galilean moons, discovered by Galileo Galilei in 1610. It is slightly smaller than Earth's moon, with a diameter of about 3,100 kilometers. From a distance, Europa looks like a creamy white billiard ball with brown streaks running across its surface. But when you look closer, you see a strange world unlike anywhere else. Europa's surface is covered with water ice, an icy crust estimated to be 15 to 25 kilometers thick. And this ice is cracked, broken, and deformed in ways that suggest something is happening beneath it. There are fractures stretching thousands of kilometers across the surface. There are regions where ice blocks seem to have separated, rotated, and reassembled like a giant puzzle. There are ridges and ice mountains hundreds of meters high. All these features indicate that the ice shell is not a solid, static block. It moves, it fractures, it renews itself, like the drifting ice on Earth's Arctic Ocean. And that suggests something remarkable. Beneath the ice lies a liquid water ocean. The evidence for this ocean comes from multiple sources. Jupiter's magnetic field generates electrical currents in conductive materials. NASA's Galileo spacecraft, during its flybys of Europa, detected fluctuations in the magnetic field that indicate the presence of a salty layer highly conductive beneath the surface. Modeling of tidal forces from Jupiter also shows that Europa must contain a liquid layer inside. As Europa orbits Jupiter along a slightly eccentric path, gravitational forces pull and push the moon with varying intensity. These changes generate friction and heat enough to keep the water beneath the ice from freezing. Scientists estimate that Europa's ocean is about 60 to 150 kilometers deep, much deeper than the deepest oceans on Earth. The total amount of water in this ocean could be 2 to 3 times greater than all the water in Earth's oceans combined. Think about that. A moon smaller than ours contains more water than the entire planet Earth. But what matters is not just the presence of water. What matters is that the water may have conditions capable of supporting life. At the bottom of Europa's ocean, where the water meets the moon's rocky core, there may be hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water emerges from cracks in the crust. On Earth, these vents are oases of life, supporting rich ecosystems in complete darkness, independent of sunlight. Bacteria use chemical energy from minerals in the hot water to produce food, forming the base of entire food chains. If Europa has similar vents, it could host life microbes and possibly more complex organisms living in eternal darkness beneath the ice. And there is evidence suggesting that water from the ocean sometimes makes its way to the surface. The Hubble Space Telescope has observed plumes of water vapor erupting from Europa's surface, massive geysers that shoot water up to 200 kilometers into space before falling back down. These plumes are not always present. They seem to appear when tidal forces from Jupiter reach their peak, temporarily opening cracks in the ice. If we could fly through one of these plumes and collect samples, we could analyze ocean water without drilling through tens of kilometers of ice. That is one of the goals of future missions to Europa. NASA is planning the Europa Clipper, a spacecraft that will be launched to study Europa in detail, making multiple flybys, mapping the surface, measuring the thickness of the ice shell, and searching for plumes. Europa is one of the most promising places to search for life in the solar system. Now let's move to another moon, smaller, but possibly even more promising. Enceladus. Enceladus is a small moon of Saturn, only about 500 kilometers in diameter, small enough to fit within the state of Arizona. From a distance, it looks like a pristine white snowball, reflecting nearly 100% of the sunlight that hits it. It is one of the brightest objects in the solar system. But in 2005, NASA's Cassini spacecraft flew past Enceladus and discovered something completely unexpected. From the south polar region of Enceladus, from a series of large fractures known as tiger stripes, enormous plumes of water and ice particles are being ejected into space. These plumes erupt continuously, shooting water up to 500 kilometers high, much higher than those on Europa. Some of the water falls back to the surface as snow, but some escapes Enceladus's weak gravity and drifts into space, forming a faint ring around Saturn known as the E-ring. The E-ring is Saturn's widest and outermost ring, and it is entirely supplied by the plumes from Enceladus. This tiny moon is slowly losing water into space, creating an icy ring around the planet. Cassini flew through these plumes, sampled the water, and analyzed it, and what it found was remarkable. The water contains salts, sodium chloride, like the salt in Earth's oceans. It contains complex organic compounds, molecules made of carbon, hydrogen, nitrogen, and oxygen, the building blocks of life. And later analysis revealed something even more important: molecular hydrogen. This hydrogen may come from chemical reactions between hot water and rock at the seafloor, exactly the kind of reactions that occur at hydrothermal vents on Earth, providing energy for microbes. Enceladus has all the ingredients necessary for life: liquid water, chemical energy, and organic compounds. And unlike Europa, where we would need to drill through ice to access the ocean, Enceladus is actively spraying its ocean contents into space, ready for us to sample. A future mission could fly through these plumes with more advanced instruments, searching for direct signs of life biomolecules, amino acids, or even microbial cells. Enceladus is small, distant, and cold, but beneath its pristine white ice may lie a warm, dark ocean where extraterrestrial microbes could be living and reproducing, completely unaware of sunlight, completely unaware of us. Now, let's move to Ganymede, the largest moon in the entire solar system. Ganymede is larger than the planet Mercury, with a diameter of 5,268 kilometers. If it orbited the Sun instead of Jupiter, it would be classified as a planet. Ganymede's surface is a strange mix of dark, ancient regions heavily scarred by impacts and brighter areas with grooves and ridges that indicate past geological activity. But the most interesting part of Ganymede lies beneath the surface. Ganymede has a subsurface ocean, but not just one. It may have multiple layers of oceans alternating with layers of high-pressure ice. Imagine a layered cake, a top ice crust about 150 kilometers thick. Beneath it, a liquid water ocean. Below that ocean, another layer of ice, but this is high-pressure ice, with a structure different from ordinary ice. Beneath that, possibly another ocean, and perhaps another ice layer. And finally, at the center, a rocky core. Ganymede may have an internal structure like a giant sandwich, with multiple layers of water and ice stacked on top of each other. This structure exists because the extreme pressure deep inside Ganymede creates different forms of ice with crystal structures, unlike the ordinary ice we know. Some forms even denser than liquid water, causing them to sink rather than float. And Ganymede has another unique feature. It has its own magnetic field. Most moons do not have magnetic fields. They are too small. Their cores have cooled and solidified. But Ganymede has a liquid iron core that is still hot and moving, generating a weak but measurable magnetic field. This makes Ganymede unique. It is the only moon in the solar system with its own intrinsic magnetic field. This magnetic field interacts with Jupiter's powerful magnetic field, creating a mini magnetosphere around Ganymede, a protective bubble that shields part of its surface from the intense radiation of Jupiter. Ganymede's ocean may contain more water than Earth, but due to the extremely high pressure and complex layered structure, the environment may not be as favorable for life as Europa or Enceladus. However, we do not yet know for certain. There may be forms of life adapted to high pressure or living at the boundaries between layers of ice and water. And now, let's talk about Callisto, the fourth Galilean moon of Jupiter. Callisto is similar in size to Mercury, only slightly smaller than Ganymede, but geologically, it is very different. Callisto's surface is the oldest in the entire solar system. It is covered with impact craters more than any other object we know. Every inch of its surface has been struck multiple times over the past 4 billion years. Unlike the other Galilean moons, Callisto shows no clear signs of recent geological activity. There are no young, smooth regions, no volcanoes. Its surface looks almost exactly as it did 4 billion years ago. But beneath that ancient surface, Callisto may also hide a secret, an ocean, The evidence is less clear than for Europa or Enceladus, but magnetic field analysis suggests that Callisto may have a salty layer deep beneath its surface, possibly at a depth of 100 to 200 kilometers. If this ocean exists, it would be extremely ancient, undisturbed by geological activity for billions of years. It would be a primordial ocean, potentially preserving chemistry from the early solar system. Studying such an ocean could give us insight into conditions in the early solar system. And finally, let's talk about Titan, a world entirely different. Titan is Saturn's largest moon, and the second largest moon in the solar system, after Ganymede. But what makes Titan special is not its size. Titan has an atmosphere, not just a thin atmosphere like Earth's moon once had. Titan has a thick, dense atmosphere, in fact, denser than Earth's. The surface pressure on Titan is about 50% higher than at sea level on Earth. This atmosphere is mostly nitrogen, 95% similar to Earth. The rest is methane and other hydrocarbons. And this atmosphere creates weather. On Titan, there are clouds. There is rain. There is wind. There are rivers flowing into lakes and seas. But this is not water. On Titan, with a surface temperature of about minus 180 degrees Celsius, water is frozen as hard as rock. Instead, the liquid cycle is based on methane and ethane. Methane clouds form in the atmosphere. Methane rain falls. Methane rivers flow through valleys carved over millions of years, and they empty into lakes and seas of liquid methane. Titan has lakes and seas, hundreds of them mapped by the Cassini spacecraft using radar. Some lakes are small, only a few kilometers across. Others are vast seas, larger than the Great Lakes of North America. Kraken Mare, the largest sea on Titan, covers about 400,000 square kilometers, larger than the Caspian Sea on Earth. In some places, it is more than 100 meters deep, filled with liquid methane and ethane. Titan is the only place in the solar system, besides Earth, with stable liquids on its surface. And Titan also has a water ocean, but not on the surface. Beneath a thick icy crust, at a depth of about 50 to 100 kilometers, Titan may have a liquid water ocean mixed with ammonia. So, Titan has two liquid systems: liquid methane on the surface and liquid water deep below. And the chemistry on Titan is extremely complex. Sunlight and radiation from Saturn's magnetic field interact with the atmosphere, producing hundreds of complex organic compounds, tholins. These compounds fall to the surface like a kind of chemical rain, accumulating over billions of years. Some scientists think Titan resembles early Earth before life began. It has a nitrogen-rich atmosphere, complex organic chemistry, and liquid on its surface. If we can study Titan, we may learn something about how life could have begun on Earth. And there is a fascinating possibility. There may be life on Titan, but not water-based life. There could be forms of life that use liquid methane instead of water, using hydrocarbon chemistry instead of water chemistry. That would be life completely unlike anything on Earth, truly alien life, showing us that biology is not limited to a single type of chemistry. All of these moons, Europa with oceans twice that of Earth, Enceladus spraying water into space, Ganymede with layered oceans, Callisto with an ancient ocean, and Titan with methane seas and prebiotic chemistry remind us that water and life-supporting conditions may be more common than we once thought. We once believed that life required an Earth-like planet orbiting a star at just the right distance. But perhaps life does not need sunlight. Perhaps it only needs liquid water, energy, and time. And these ocean moons have all three. While some moons hide quiet oceans beneath ice, others are worlds of fire, violence, and uncontrollable energy. There are moons where volcanoes erupt lava higher than any mountain on Earth. There are moons that look as if they have been torn apart and clumsily reassembled. There are moons with colors no one can fully explain. These worlds remind us that moons are not just cold, dead rocks. Some are alive with energy, shaped by powerful forces and constantly changing. Let's begin with the most volcanically active world in the entire solar system, Io. Io is the innermost Galilean moon of Jupiter, orbiting the gas giant at a distance of about 422,000 kilometers, slightly farther than the distance between Earth and our moon. From a distance, Io looks like a cosmic pizza, a sphere of yellow, orange, and red, with patches of white, brown, and black scattered across its surface. There is no blue or green, no sign of water or ice. And when spacecraft approached closer, they discovered why Io has such strange colors. Its entire surface is covered with sulfur and sulfur compounds from hundreds of active volcanoes. Io has more than 400 active volcanoes, more than any other world in the solar system, including Earth. These volcanoes are not like those on Earth. They are far more powerful, far more violent. Some volcanoes on Io eject lava up to 300 or even 400 kilometers into space. By comparison, the most powerful volcanic eruptions on Earth rarely propel material more than a few dozen kilometers high. Why does Io have such extreme volcanic activity? The answer is tidal forces. Io orbits very close to Jupiter, and it is squeezed between the immense gravity of Jupiter on one side and the gravitational pull of two other Galilean moons, Europa and Ganymede, on the other. These three moons are locked in an orbital resonance, a repeating pattern, where for every orbit Ganymede makes around Jupiter, Europa completes 2 and Io completes 4. This ratio, 1 to 2 to 4, creates a complex gravitational dance. As a result, Io is constantly being pulled and pushed in different directions. Its orbit is slightly eccentric, meaning its distance from Jupiter changes slightly as it moves. When it is closer, gravity is stronger. When it is farther away, it is weaker. This variation stretches and compresses Io like a rubber ball being squeezed repeatedly. Io's surface rises and falls by up to 100 meters each day, as if the entire moon is breathing. And the friction from this constant deformation generates enormous heat. Enough heat to melt rock inside Io. Enough heat to create vast magma oceans beneath the surface. Enough heat to power hundreds of continuously erupting volcanoes. Io does not have a hot radioactive core like Earth. All of its heat comes from tidal forces from being distorted by gravity. And this volcanic activity constantly renews Io's surface. Each eruption covers older regions with fresh lava. Scientists estimate that Io's entire surface is resurfaced every few million years, a very short time on geological scales. That is why Io has no impact craters. Any crater formed by meteoroids is quickly buried under new lava. Io's surface is the youngest in the solar system, continuously renewed by fire and lava, and temperatures on Io are extreme. Most of the surface is cold, around minus 130 degrees Celsius, since Io is far from the sun. But at volcanic vents, temperatures can reach up to 1,600 degrees Celsius hotter than lava on Earth. Some volcanoes erupt sulfur-rich silicate lava. Liquid sulfur displays different colors depending on temperature: yellow when freshly erupted, turning orange, red, and eventually brown and black as it cools. That is why Io looks like a chaotic palette of colors. Lava flows on Io can extend for hundreds of kilometers. One flow observed by the Galileo spacecraft was more than 300 kilometers long, longer than any known lava flow on Earth. And Io has an atmosphere, but not one you could breathe. It is extremely thin, composed mainly of sulfur dioxide gas released by volcanoes. This atmosphere freezes and falls to the surface like snow at night, then sublimates again during the day when the sun rises. If you stood on Io, you would witness an unimaginable scene. The sky would be black because the atmosphere is too thin to scatter light. Jupiter would dominate nearly half the sky, a massive striped sphere, more than 40 times larger than the moon as seen from Earth. And around you, plumes of lava and gas would erupt into space, forming glowing arcs against the black sky. The ground beneath your feet would warm and cool as you move between volcanic and colder regions. Everything would be colored in yellow, orange, and red, as if standing inside a wild, abstract painting. Io is a volcanic hell, but it is also one of the most dynamic and fascinating worlds in the solar system. Now, let's move to a completely different world, a small, distant moon of Uranus, Miranda. Miranda is only about 470 kilometers in diameter, small enough to fit within Texas. It is one of the 5 major moons of Uranus, the ice giant that lies tilted on its side in its orbit. When Voyager 2 flew past Miranda in 1986, the only time we have visited the Uranus system, scientists were astonished by what they saw. Miranda's surface looks as if it has been torn apart and clumsily stitched back together by a giant child playing with clay. There are ancient, heavily cratered regions that resemble most other moons, but right next to them are areas that look completely different: oval or V-shaped coronae with parallel grooves, steep cliffs, and complex terrain. The 3 largest coronae: Corona, Elsinore corona, and Inverness corona, look like pieces that do not quite fit with the rest of the surface. How did Miranda get such a strange appearance? One hypothesis is that Miranda was shattered and reassembled multiple times. In the distant past, Miranda may have been struck by an asteroid or another moon. The impact could have broken it into large fragments, but these fragments did not escape the system. Instead, Uranus's gravity held them, and over time, they came back together. As the pieces reassembled, they did not fit perfectly. Some were hotter than others. Some were deformed during reaccretion. The result is a moon that looks like a broken object glued back together carelessly. Another hypothesis is that the coronae are the result of past geological activity, possibly warm ice rising from the interior, creating grooves and cliffs as it cooled and contracted. Whatever the cause, Miranda has some of the most dramatic terrain in the solar system. In particular, it has Verona Rupes, the tallest known cliff in the solar system. Verona Rupes is a vertical cliff about 10 to 12 kilometers high, nearly twice the height of Mount Everest from sea level. It is a near vertical wall of ice and rock stretching for tens of kilometers. If you stood at the top of Verona Rupes and looked down, you would see a 12-kilometer drop below. And because Miranda's gravity is extremely weak, only about 1/80th of Earth's, if you jumped off the edge, you would fall for about 12 minutes before reaching the bottom. 12 minutes of free fall. Enough time to read a chapter of a book or eat a meal while slowly accelerating toward the distant icy surface below. Of course, when you hit the ground, even with weak gravity, the speed accumulated over 12 minutes would still be enough to kill you. But at least you would have time to enjoy the view on the way down. Miranda is distant, and cold surface temperatures are around -200 degrees Celsius. But it is a reminder that even the smallest moons can have violent and complex histories. And now, let's talk about one of the most visually strange moons, Iapetus. Iapetus is the third largest moon of Saturn, with a diameter of about 1,470 kilometers. It orbits far from Saturn, more than 3.5 million kilometers away, much farther than the other major moons. And when astronomers first observed Iapetus through telescopes, they noticed something strange. Its brightness changes dramatically as it orbits Saturn. Initially, Triton's orbit may have been highly eccentric, an elongated ellipse that brought it close to Neptune and then far away. But over millions of years, tidal forces from Neptune gradually circularized the orbit, pulling it into a more stable, round path. This process generated enormous heat inside Triton, the same kind of tidal heating that makes Jupiter's a volcanic world. In the early period after its capture, Triton may have been extremely hot, with a vast liquid water ocean beneath its surface. Over time, as the orbit stabilized, tidal heating decreased. The ocean froze. Triton cooled. But even today, Triton still bears traces of that violent past. When Voyager 2 flew past Triton in 1989, it revealed a world unlike any other. Triton's surface appears young, with far fewer impact craters than most moons. It has strange terrain, known as cantaloupe terrain, depressions and ridges forming patterns that resemble the skin of a cantaloupe melon. Most remarkably, Voyager 2 observed geysers, jets of nitrogen gas erupting up to 8 kilometers into the thin atmosphere. Triton is still geologically active, driven by weak sunlight at that great distance, and possibly some residual tidal heating. But Triton's long-term fate is already sealed. Because of its retrograde orbit, the tidal interaction between Triton and Neptune behaves differently from that of prograde moons. Instead of pushing Triton away, as Earth's moon is gradually moving away from us, tidal forces are pulling Triton closer to Neptune. Each century, Triton moves slightly closer. The process is extremely slow, but irreversible. In about 3.6 billion years, a long time, but not forever, Triton will come too close to Neptune. At that point, tidal forces will become overwhelming. Triton will cross the Roche limit, the distance at which a planet's tidal forces exceed the self-gravity holding a moon together, and Triton will be torn apart. It will not explode suddenly. Instead, over millions of years, it will gradually disintegrate. Fragments will break off. The surface will fracture. Eventually, the entire moon will shatter into thousands of pieces. These fragments will spread out, forming a ring around Neptune. A vast, magnificent, beautiful ring system made from the remains of a captured dwarf planet from billions of years ago. Neptune currently has faint, dark rings, but when Triton is destroyed, it will gain a spectacular ring system, perhaps even more impressive than Saturn's. Triton is a tragic story, a world that was once free, traveling through space, captured by a giant planet, forced into an orbit that ends in destruction. But Triton is not alone in this fate. Mars's moon, Phobos, as we discussed, is also spiraling inward and will be torn apart in tens of millions of years. And there are dozens of other small moons awaiting similar destinies. Around Jupiter, there are at least 95 known moons, some large, like Ganymede and Europa, but most much smaller, only a few kilometers in diameter. These small moons are grouped based on their orbits. There are the Himalaya group, the Carme group, the Ananke group, the Pasiphae group, each containing between 5 and 20 small moons with similar orbital characteristics. Most of these moons have retrograde and highly eccentric orbits. They orbit very far from Jupiter, some at distances greater than 20 million kilometers, so far that their orbital periods exceed 2 Earth years. These are clearly captured asteroids, and the fact that they are grouped suggests that each group may once have been a larger parent body that was broken apart, either by collisions with other asteroids or by Jupiter's tidal forces. Saturn has a similar collection. Beyond its well-known large moons like Titan and Enceladus, it has more than 80 smaller moons, many with unusual orbits indicating captured origins. Phoebe, one of these moons, is particularly interesting. It orbits Saturn in a retrograde direction at a great distance, over 12 million kilometers away. Its composition resembles Kuiper Belt objects more than typical Saturnian moons. Phoebe may be a small dwarf planet-like body from the Kuiper Belt captured by Saturn long ago, similar to Triton, but much smaller. And as mentioned, Phoebe is slowly being eroded. Meteorite impacts eject small fragments, forming a diffuse cloud of dark dust along its orbit. Some of this dust eventually drifts into Iapetus's orbit, contributing to the dark hemisphere of that moon. Uranus and Neptune also have their own collections of captured moons, small worlds with unusual orbits pointing to distant origins. All of these moons, from the giant Triton to countless small asteroid-like bodies orbiting the gas giants, tell the story of a dynamic solar system where objects move, orbits change, and chance encounters produce dramatic outcomes. Billions of years ago, in the chaotic early days of the solar system, when planets were still migrating into their final positions, there may have been thousands or tens of thousands of such capture events. Most captured moons may have fallen into their planets or been ejected from the system. Only a few, lucky or unlucky, depending on perspective, survive today. And each captured moon carries a story of once being free, wandering through space, being captured by gravity, and bound to a new fate. Some, like Triton, are slowly moving toward a violent end. Others may survive for billions more years, quietly orbiting at the edges of their planetary systems. But all of them remind us that in the universe, nothing is permanent. Orbits change. Worlds move. What was once free can become bound. What was once stable can be destroyed. Gravity does not just hold moons in orbit. It creates complex dances, subtle interactions, and strange phenomena that have taken centuries for scientists to understand. Some moons are locked together in ways that seem impossible. Some create repeating patterns with clockwork precision. Some interact with planetary rings, sculpting them into beautiful and intricate structures. This is where gravity becomes art. Let's begin with one of the strangest dances in the solar system, the dance of Janus and Epimetheus. These two small moons orbit Saturn at nearly identical distances. Janus is about 180 kilometers in diameter. Epimetheus is slightly smaller, about 120 kilometers, and their orbits are separated by only about 50 kilometers, an extremely small distance on a cosmic scale. Normally, two moons on such close orbits would either collide or one would eject the other from orbit. But Janus and Epimetheus do neither. Instead, they perform a perfectly choreographed dance. At any given time, one moon orbits Saturn on the inner path, closer to the planet, while the other follows an outer orbit slightly farther away. The moon on the inner orbit moves faster. That's how orbital mechanics works. The closer you are to a planet, the faster you travel. So gradually, it catches up to the moon on the outer orbit. You might expect a collision, but something remarkable happens when they get close. When the two moons come within a few hundred kilometers of each other, their mutual gravity begins to interact. The inner moon, moving faster, is pulled backwards slightly by the gravity of the outer moon. This causes it to lose orbital energy, and its orbit expands, pushing it farther out. At the same time, the outer moon, moving more slowly, is pulled forward slightly by the gravity of the inner moon. This gives it additional orbital energy, but in the strange rules of orbital mechanics, gaining energy in an outer orbit actually causes it to move inward. So within a short period, just a few hours, the two moons exchange orbits. The one that was inside moves to the outside. The one that was outside moves inward. They never collide. They simply swap places, like two dancers spinning around each other in a perfectly timed routine. And then the process repeats. Now, the moon in the inner orbit, the one that just moved there, begins to catch up with the one now in the outer orbit. After about 4 Earth years, they meet again and exchange orbits once more. This dance has continued for millions of years and will continue for millions more. Janus and Epimetheus are locked in an eternal gravitational tango, never touching, always exchanging positions. No other pair of moons in the solar system behaves like this. It is a unique arrangement, an accident of history that produces a beautiful phenomenon. And there are other strange interactions between moons. The Galilean moons of Jupiter, Io, Europa, and Ganymede, are locked in an orbital resonance, as we discussed. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This ratio, 1 to 2 to 4, is not a coincidence. It is the result of millions of years of gravitational interactions gradually pulling the moons into this configuration. This resonance has important consequences. It keeps the orbits of Io, Europa, and Ganymede slightly eccentric, not perfectly circular. And these eccentric orbits create varying tidal forces, generating tidal heating. For Io, the result is extreme volcanic activity. For Europa and Ganymede, the result is enough heat to maintain liquid oceans beneath their icy crusts. So, this gravitational dance is not just a mathematical curiosity. It fundamentally shapes the physical nature of these worlds. And some moons rotate extremely slowly. Most large moons are tidally locked to their planets, meaning their rotation period equals their orbital period. This causes the same face to always point toward the planet. But some small moons are not tidally locked, and a number of them rotate extremely slowly. Hyperion, the porous moon of Saturn we discussed earlier, not only tumbles chaotically, but also rotates very slowly. Its average rotation period is about 13 days, though it varies unpredictably. Some small moons of the gas giants take weeks or even months to complete a single rotation. And there is an even stranger phenomenon. Some asteroids and very small moons rotate so slowly that they seem almost motionless. This happens when a small, irregularly shaped body rotates in an environment where tidal forces or other gravitational interactions create torques that gradually slow its rotation. Some asteroids in the asteroid belt take months to complete one rotation on their axis, an extremely slow rate compared to most objects in the solar system. Now, let's talk about one of the most powerful interactions. When a moon is torn apart by tidal forces, every planet has a Roche limit. The distance within which tidal forces from the planet exceed the gravity holding a moon together. This limit depends on the density of the planet and the density of the moon. For Saturn, with typical icy moons, the Roche limit lies at about 150,000 kilometers from the planet's center. And if you look at Saturn's ring system, you'll notice something remarkable. The rings lie entirely within the Roche limit. This is not a coincidence. Rings are what happens when a moon gets too close. Scientists are not certain how Saturn's rings formed, but there are two main hypotheses. One is that the rings are the remnants of a moon that once orbited just outside the Roche limit, but gradually moved inward due to tidal forces or collisions. When it crossed the Roche limit, it was torn apart into billions of fragments, forming the rings. The other is that the rings were never a moon. Instead, they are material from the primordial cloud that formed Saturn, which never accreted into a moon because it lay within the Roche limit, where tidal forces prevent accumulation. Either way, the result is one of the most beautiful structures in the solar system. Saturn's shimmering rings, made of billions of particles of ice and rock, each orbiting the planet on its own path. And moons interact with these rings in subtle and complex ways. Some moons, called shepherd moons, orbit just inside or outside the rings and use their gravity to keep the rings confined and sharply defined. Prometheus and Pandora are two such shepherd moons that orbit on either side of Saturn's F ring, one of the outermost rings. Prometheus orbits inside the ring, Pandora outside. The gravity of Prometheus pulls ring particles outward, while Pandora's gravity pulls them back in. The result is that the F ring is kept in a narrow band, even though it lies relatively far from Saturn, where rings would normally spread and dissipate. But the interaction is not simple. Prometheus does not follow a perfectly circular orbit, and as it moves closer to and farther from the F ring, its gravitational influence changes. This creates kinks and strands, twists and filaments in the F ring, producing a braided, ever-changing structure. Pan, the ravioli-shaped moon we discussed, is another type of shepherd moon. It orbits within the Encke gap in Saturn's ring's A ring, and its gravity keeps this gap clear, sweeping ice particles out of its path. But Pan does more than just keep the gap clean. As it moves, it creates waves, ripples in the ring material on either side of the gap. These waves spread out from Pan like the wake behind a boat, forming intricate patterns that can be seen in close-up images of the rings. Daphnis, a smaller moon that also orbits within a gap of the A ring, the Keeler gap, creates even more beautiful waves. These waves are not symmetrical. They are higher on one side of the gap than the other, because Daphnis's orbit is slightly inclined relative to the plane of the rings. The result is a series of peaks and troughs running along the edge of the gap, resembling waves frozen in motion. And there is another type of interaction: orbital resonance between moons and ring particles. Mimas, the Death Star-like moon, orbits Saturn with a period of about 22.6 hours. And there is a region in the A ring where ice particles orbit Saturn with a period exactly half that of Mimas, about 11.3 hours. This means that every time Mimas completes one orbit, those particles complete two. And every two orbits, they return to the same relative position with respect to Mimas. This creates a repeated gravitational tug, always at the same point in the particle's orbit. Over time, these small tugs accumulate, altering the particle's orbit and pushing it out of the resonance region. The result is a gap in the A ring known as the Cassini division, a nearly 5,000-kilometer wide region where the particle density is much lower than in the surrounding areas. This gap is not completely empty. There are still some particles there. But it is distinct enough to be seen from Earth with a small telescope, giving Saturn's rings their characteristic appearance as multiple separate rings rather than a continuous disk. Other resonances with moons such as Enceladus, Tethys, and Dione create additional gaps and structures within the rings. The entire ring system of Saturn is shaped by gravitational forces from its moons, a complex symphony of gravitational interactions that create structure, patterns, and beauty. And it's not just Saturn. All the gas giant planets have rings, though none are as striking and well-defined as Saturn's. And all of these rings are shaped by interactions with moons. Jupiter has a thin ring formed from material knocked off its four inner moons, Métis, Adrastee, Amalthea, and Thebe, by meteoroid impacts. Uranus has dark, narrow rings held in place by small shepherd moons. Neptune has incomplete rings with arcs, denser segments, maintained by resonance with the moon Galatea. Everywhere we look, we see gravity writing patterns, creating structure, choreographing dances between moons and particles, between moons and planets, and between moons themselves. And these interactions are not static. They evolve. Moons move inward or outward. Orbits change. New resonances form. Old ones break apart. The solar system is a living, breathing, dynamic system where gravity is the conductor, orchestrating a complex symphony that we are only beginning to fully understand. Each moon is a musician in this orchestra, contributing its own part to the overall composition. Some perform dramatic solos, some blend into delicate duets, some are part of larger ensembles, creating complex harmonies. And the dance continues. It has continued for billions of years, and it will continue for billions more, long after we are gone. For centuries, when we thought about life beyond Earth, we looked to planets. We searched for Earth-like worlds orbiting sun-like stars, at the right distance to allow liquid water on the surface. But in recent decades, our understanding has shifted profoundly. Perhaps the most promising places to search for life in the solar system are not planets. Perhaps they are moons. And perhaps life does not need sunlight, blue skies, or warm, comfortable surfaces. Perhaps all life needs is liquid water, energy, and time. And some moons in the solar system have all three. Let's begin with the three basic ingredients that life, at least life as we know it, appears to require. First is liquid water. Water is the universal solvent, where molecules dissolve and interact, where the chemistry of life can occur. On Earth, every form of life we know requires water. Even the most extreme organisms, bacteria living in dry deserts, in Antarctic ice, deep within rocks underground, all require at least some water. Second is energy. Life needs energy to maintain order, to repair damage, and to reproduce. On Earth, most energy comes from the sun through photosynthesis, but not all. In the deep ocean, where there is no light, life depends on chemical energy from hydrothermal vents, where hot, mineral-rich water erupts from beneath the seafloor. Third are the right chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the building blocks of complex organic molecules such as proteins, nucleic acids, and lipids. And remarkably, some moons in the solar system have all three. Europa, as we discussed, has a vast ocean beneath its icy crust. This ocean may be 100 kilometers deep or more, containing twice as much water as all of Earth's oceans combined. And this water does not freeze because there is energy. Tidal forces from Jupiter pull and squeeze Europa, generating friction and heat inside the moon. This heat keeps the ocean liquid, even though Europa is more than 5 times farther from the sun than Earth. At the bottom of Europa's ocean, where water meets the rocky core, there may be rich chemistry. As water interacts with rock under high temperature and pressure, chemical reactions occur, releasing dissolved elements into the ocean. And if hydrothermal vents exist, as many scientists believe is likely, then Europa would have all the necessary ingredients for life. Spectral analyses of Europa's surface show traces of salts, sodium chloride, like table salt, and sulfur compounds. These substances may come from the ocean below, brought to the surface through cracks and plumes. If so, that would mean Europa's ocean has rich chemistry, not just pure water. And there is evidence that Europa's surface is continuously renewed. Cracks and ridges suggest that the ice shell is moving, fracturing, and reshaping itself. Some regions appear as if older ice has broken apart. The pieces have rotated and shifted, and the gaps between them have been filled by water from below that later froze into place. This means there is an exchange between the surface and the ocean. Material from the surface, bombarded by radiation from Jupiter and containing organic compounds from meteorites, may sink into the ocean over time. And water from the ocean may bring nutrients up to the surface. If there is life in Europa's ocean, it may be simple microbial life, similar to bacteria at hydrothermal vents on Earth. But it could also be an entire biosphere, a complex ecosystem in complete darkness, living off chemical energy rather than sunlight. There could be organisms that feed on bacteria. There could be predators that hunt those organisms. Entire food chains could exist beneath the ice, never having seen sunlight, completely isolated from any other ecosystem in the solar system. And if we want to find out, we need to send a mission there. NASA is developing the Europa Clipper, expected to launch in the mid-2020s, which will fly past Europa multiple times, map the surface, measure the thickness of the ice, analyze any plumes, and search for signs of life. But to truly know for certain, we may need a lander mission to drill through the ice and sample the ocean. That is an enormous technical challenge, but not an impossible one. And the reward, discovering life beyond Earth, would be one of the most profound discoveries in human history. Enceladus, in many ways, may be even more promising than Europa. As we discussed, Enceladus is ejecting material from its ocean into space through massive plumes at its south pole. An analysis of these plumes has revealed remarkable findings. The water contains salt, indicating it has been in contact with rock. It contains silica, tiny silicon particles that can only form at temperatures above 90 degrees Celsius, suggesting that hot water exists somewhere within the ocean. It contains complex organic molecules, some large and heavy, with ring and chain structures. These molecules resemble prebiotic compounds on Earth, molecules that could be precursors to life. And most importantly, it contains molecular hydrogen, H2. This almost certainly comes from chemical reactions between hot water and rock on the sea floor in a process called serpentinization. On Earth, serpentinization occurs at hydrothermal vents. And at these vents, microbes use hydrogen as an energy source, combining it with carbon dioxide to produce methane and energy for life. Enceladus has all the ingredients for this same kind of chemistry. It has liquid water, it has warmth, it has hydrogen, it has carbon dioxide, it has organic compounds. In other words, Enceladus has an environment very similar to the one where life thrives on Earth. At hydrothermal vents, deep beneath the ocean. Some scientists say that if Enceladus does not have life, it would be an astonishing missed opportunity. And the remarkable thing about Enceladus is that we do not need to land or drill. We only need to fly through the plumes with the right instruments. A future mission could sample the ocean directly without ever touching the surface. Titan offers a different possibility, a different kind of prebiotic chemistry. Titan has a thick, nitrogen-rich atmosphere similar to Earth's. It has methane rain, methane rivers, lakes, and seas. It has clouds and winds and weather, and within this atmosphere, complex chemistry is constantly taking place. Sunlight and radiation from Saturn's magnetic field break apart methane and nitrogen molecules. These fragments recombine in new ways, forming hundreds of different organic compounds: ethane, propane, benzene, nitriles, amines, and more. These compounds condense into tiny particles called tholins, complex organic particles, that fall to the surface like a kind of chemical rain, accumulating over billions of years. Titan's surface is covered with these organic materials. In a sense, the entire moon is a vast natural chemical laboratory that has been running for 4 billion years. Some scientists think Titan resembles early Earth, before life began. Early Earth also had a nitrogen-rich atmosphere and complex organic chemistry in its atmosphere. Studying Titan may help us understand how prebiotic chemistry led to life on Earth. And there is a fascinating possibility. There may be life on Titan, but not life based on water. At Titan's surface temperature, around minus 180 degrees Celsius, water is as hard as rock, but methane and ethane are liquid. Could there be life forms that use liquid methane as a solvent instead of water? That would be a completely different biochemistry, life based on different molecules and reactions. But in theory, it could exist. Some scientists have modeled what kinds of cell membranes could exist in liquid methane. They call them azotosomes, membrane-like structures made from nitrogen-containing molecules that could remain stable in cold methane. If such life exists on Titan, it would be truly alien, nothing like life on Earth. It would show that life is not limited to a single type of chemistry, that the universe may be filled with unimaginably diverse forms of life. And Titan also has a subsurface ocean of water deep beneath its icy crust. So there may be two biospheres on Titan, one on the surface based on methane, and one below based on water. Two completely different forms of life on the same moon. Ganymede and Callisto, with their layered oceans and ancient oceans, are also potential candidates, though perhaps less promising than Europa and Enceladus. The extreme pressure in Ganymede's ocean and the long isolation of Callisto's ocean may make the environments less favorable, but we cannot rule out the possibility. And even Mimas, with its recently discovered hidden ocean, becomes an unexpected candidate. All of these moons, Europa, Enceladus, Titan, Ganymede, Callisto, Mimas, and perhaps others we have not yet studied in detail, represent a profound shift in how we think about life in the universe. For centuries, we searched for life on Earth-like planets. But perhaps moons with subsurface oceans are far more common than Earth-like planets. In our own solar system, we have one planet with surface oceans, Earth. But we may have 5 or 6 moons with subsurface oceans. If this ratio holds elsewhere in the universe, there could be billions of hidden oceans beneath icy surfaces of moons orbiting distant planets, And each of those oceans is an opportunity for life. This means that life may be far more common than we once thought. It doesn't need a planet in the habitable zone around a star. It only needs a moon large enough orbiting a planet massive enough to generate tidal forces that keep water in a liquid state. And those conditions could exist almost everywhere in the galaxy. Perhaps the universe is filled with hidden oceans, lying beneath icy surfaces in eternal darkness, where life evolves without ever seeing the light of a star. Perhaps we are not alone. Perhaps life is common, diverse, and resilient. And perhaps the first places where we find evidence of it will not be on the surface of a distant planet, but right here in our own solar system, beneath the ice of a small moon. We have explored the grand things: subsurface oceans, blazing volcanoes, complex gravitational dances. But moons are also filled with smaller details, strange facts, and fascinating features, each revealing a different aspect of the incredible diversity of these small worlds. Enceladus, the small moon of Saturn that we have discussed extensively, is one of the brightest objects in the entire solar system. Its surface, made of pure water ice, continuously refreshed by snow from its plumes, reflects nearly 100% of the light that strikes it. Scientists measure the albedo, reflectivity, of Enceladus at about 0.99. This means that 99% of the sunlight hitting Enceladus is reflected back into space. For comparison, fresh snow on Earth has an albedo of about 0.8 to 0.9. Enceladus is brighter than fresh snow. If you stood on the surface of Enceladus, even under the faint sunlight at Saturn's distance, you would be surrounded by brilliant reflected light. The ground beneath your feet would shine like a mirror. And if there were light from Saturn, the giant planet occupying a large portion of the sky, the reflected light from the surface would be strong enough to cast shadows. You could see your own shadow not from the sun, but from light reflected off Saturn onto the glittering ice of Enceladus. It would be a world of reflected light, where every surface is a mirror, where light bounces back and forth until the boundary between sky and ground nearly disappears in a white glow. But at the other end of the spectrum, there are moons that reflect almost no light at all. Himalaya, one of Jupiter's small moons, has a surface so dark that it reflects only about 3 to 4% of the light that hits it. Its albedo is 0.03 to 0.04, much darker than fresh asphalt. It is not alone. Many of the outer moons of the gas giants, captured moons with compositions similar to asteroids, have extremely dark surfaces. Phoebe, a moon of Saturn, is also very dark. Some moons of Uranus and Neptune are as well. These dark surfaces may be made of complex organic compounds, tholins, formed when radiation interacts with methane and other hydrocarbons. Over billions of years, these compounds accumulate, creating a dark, coal-like coating. If you stood on Himalaya, you would see the opposite of Enceladus. The ground would be as dark as night. Jupiter, though enormous in the sky, would not produce much reflected light. You would be in a nearly black world, where light seems to be absorbed and swallowed by the surface. and some moons orbit at extremely large distances from their planets, so far that they are almost independent. The outermost moons of Jupiter orbit at distances of more than 20 million kilometers. To put that in context, that is about 50 times the distance from Earth to our moon. At that distance, Jupiter's gravity is only slightly stronger than the Sun's. These moons lie at the edge of Jupiter's sphere of influence, the region of space where the planet remains the dominant gravitational force. Their orbits are extremely fragile. A gravitational interaction with a passing object or even a small perturbation from solar radiation could knock them out of orbit entirely. Some of these moons may not remain stable over billions of years. They could be ejected from Jupiter's system, becoming interplanetary wanderers, or even be captured by another planet. They are temporary moons, transient residents in Jupiter's domain, loosely held by gravity. And farther still, beyond Neptune, in the Kuiper Belt, a cold region of space filled with icy worlds, there are many dwarf planets with their own moons. Pluto has 5 known moons. Charon, the largest, is nearly half the size of Pluto. It is so large that some scientists refer to the Pluto-Charon system as a binary dwarf planet rather than a planet and a moon. Pluto's 4 other moons, Nix, Hydra, Kerberos, and Styx, are much smaller, only a few tens of kilometers in diameter. Haumea, another dwarf planet, has 2 moons, Hi'iaka and Namaka. Eris has 1 moon, Dysnomia. Makemake has a small moon that has not yet been officially named, and there may be hundreds or thousands of other dwarf planets in the Kuiper Belt and beyond, many of which could have their own moons. Most of these moons are unnamed. They are labeled with dry, numerical designations. They have never been visited by spacecraft. We know they exist only as faint points of light in telescope images. Each is its own world, with its own history, composition, and surface. But most will never be studied in detail. They are too distant, too small, too dim. They are anonymous moons, hidden worlds, quietly orbiting in the darkness at the edge of the solar system. And there is something curious about how moons are named. Most planets name their moons after mythological figures. Jupiter's moons are named after the lovers and children of Zeus in Greek mythology. Saturn's moons are named after the Titans and other deities. Neptune's moons are named after sea gods and marine creatures. But Uranus does something different. Its moons are named after characters from the works of William Shakespeare and Alexander Pope. Titania and Oberon, the king and queen of the fairies from A Midsummer Night's Dream. Ariel and Umbriel from Pope's The Rape of the Lock. Miranda from The Tempest. Puck from A Midsummer Night's Dream. Ophelia and Cordelia from Hamlet and King Lear. No other planet does this. It is a unique tradition that began with the astronomer William Herschel, who discovered Uranus and has continued ever since. So when we talk about the moons of Uranus, we are talking about literary characters, princes and princesses, fools and spirits, tragic lovers, and brave heroes, all orbiting an icy giant planet in the cold darkness of the outer solar system. And speaking of things that last a long time, let's return to Earth's moon. When the Apollo astronauts stepped onto the lunar surface in the 1960s and 1970s, they left footprints in the lunar dust, regolith. Those footprints are still there today. perfect, unchanged, exactly as they were when they were made more than 50 years ago. And they will still be there for millions of years to come. On Earth, footprints disappear quickly. Wind blows sand to cover them. Rain washes them away. Plants grow through them. Within hours, days, or at most a few years, they are gone. But on the moon, there is no wind, no rain, no plants, no weather to erase the traces. Only two things can change the lunar surface: meteorite impacts and radiation from the sun. But both are extremely slow. Small meteorites strike the moon, but the surface is vast, and impacts are random. It would take millions of years before a meteorite happened to hit exactly where a footprint lies. Radiation from the sun gradually weathers the surface, altering the color of the regolith over thousands of years. But it does not fill in the footprints. So those footprints, the first images of humans on another world, will outlast any monument we build on Earth, outlast any city, outlast perhaps humanity itself. Millions of years into the future, if humanity no longer exists, if Earth has changed beyond recognition, those footprints will still be there. The fossil traces of our species, evidence that once we came here. And there is one final truth, more wondrous still. Some moons are still being born. Right now, within the rings of Saturn, processes are underway that may be creating new moons. Scientists have observed ripples and disturbances in the rings, patterns suggesting that small objects are forming from ring particles. These moonlets, tiny moons, may be only a few hundred meters in diameter. They are born as ring particles collide and stick together, slowly accumulating mass. Most of these moonlets are not stable. They will be torn apart by tidal forces or destroyed by collisions with other particles. But some may survive long enough to migrate out of the rings, where they are safer from destruction. Over millions of years, a lucky moonlet may gradually grow, accumulating more material and eventually become a true moon. Some of Saturn's smaller moons may have formed in exactly this way. Pan and Daphnis, moons that orbit within gaps in the rings, may have been born inside the rings and then cleared the gaps around them. And this process may still be ongoing. In Saturn's F ring, scientists have observed objects temporarily appearing and disappearing, possibly small moonlets forming and being destroyed in a continuous cycle. Saturn's rings are not merely a static structure. They are a dynamic, living environment where creation and destruction occur constantly. And further into the future, as the rings continue to evolve, new moons may yet be born. Worlds we have never seen, made from the material of the rings, the children of Saturn still yet to come. All these small truths, from Enceladus bright as a mirror to Himalaya dark as coal, from distant moons nearly independent to those not yet named in the Kuiper Belt, from Apollo footprints that will endure for millions of years to moons being born in Saturn's rings, together paint a rich, complex, and endlessly surprising picture. Moons are not simply objects orbiting planets. They are diverse worlds, each with its own story, its own character, its own fate. They are bright and dark, near and far, ancient and newly born. They are named after mythology and literature. They carry the traces of humanity and the traces of billions of years of cosmic history. And each one, in its own way, is a wonder. Breathe deeply. Let the body rest. Let the shoulders relax completely. Let the mind drift gently through these images. Gleaming ice, surfaces dark as night, a solitary footprint in cosmic dust, tiny moons being born in glittering rings. And know that out there, the solar system is full of small wonders, fascinating truths, beautiful details waiting to be discovered. We have traveled a long journey through the moons of the solar system. From Earth's moon, that ancient companion slowly drifting away from us, carrying with it secrets of its violent origins and its vital role in keeping Earth's climate stable. To the strange small moons, Phobos falling toward its inevitable death, pan-shaped like a ravioli, carving a gap in the rings, Hyperion tumbling in unpredictable chaos, Mimas resembling the Death Star with its secret ocean. To the vast subsurface oceans, Europa holding twice Earth's water hidden beneath ice, Enceladus spraying its ocean's contents into space, Ganymede with layers of ice and water stacked like a multi-tiered cake, Titan with an atmosphere thicker than Earth's, and methane seas beneath a hazy orange sky. To the worlds of fire, Io with volcanoes erupting lava hundreds of kilometers high, its surface continuously remade by fire and sulfur. Miranda with a cliff 12 kilometers tall, where you would fall for 12 minutes. Iapetus half white as snow, half black as coal, with a mountain range running along its equator. To the captured wanderers, Triton, once a free dwarf planet, now orbiting in reverse, and slowly spiraling toward the day it will be torn into rings. Small asteroids pulled into orbit around the gas giants, becoming moons without a choice. To the wondrous gravitational dances, Janus and Epimetheus exchanging orbits every 4 years in a perfect cosmic tango. Shepherd moons sculpting the rings into beautiful shapes, orbital resonances carving distinct gaps in Saturn's rings, to the possibility of life, dark oceans where bacteria may live off chemical energy, where complete ecosystems may exist in eternal darkness, where liquid water, thermal energy, and organic chemicals converge, creating conditions for life to emerge. And to the small, strange truths, Enceladus bright as a mirror, Himalaya dark as coal, footprints on the moon that will endure for millions of years, new moons being born in Saturn's rings right now. From moons as small as cosmic pebbles to Ganymede, larger than the planet Mercury. From moons shaped like potatoes, like ravioli, like walnuts, to nearly perfect spheres. From ancient surfaces unchanged for 4 billion years to surfaces remade every few years by geological activity. Each moon is a story of formation, of evolution, of collision and capture, of volcanoes and ice, of light and darkness, of solitude in vast space. The moons show us that the solar system is not a static collection of dead objects following predictable orbits. It is a living, dynamic place, full of activity, where volcanoes erupt, where oceans slosh beneath ice, where moons exchange orbits, where life may be thriving in the darkness, where some moons are falling toward their death, and others are being born, where history is written in fire and ice, in collision and gravity, in time and chance. And all of this happens silently, unwitnessed, at vast distances. Io erupts lava higher than any mountain on Earth, but there is no one there to hear the explosion. Enceladus sprays water into space, but there is no one there to see the glittering plumes. Moons orbit one another in complex dances, but there is no audience to admire the beauty of the ballet. Only our spacecraft, those tiny robotic messengers, have visited some of them, capturing fleeting images, sending data home, and then flying off into the darkness. But those fleeting glimpses have changed our understanding of the solar system. They have shown us that the diversity of worlds far exceeds our imagination, that each moon, however small, has a story worth telling. And perhaps most importantly, they have shown us that we may not be alone, that life may exist in places we never imagined, not on Earth-like planets, but in the hidden oceans of distant moons. That right now, in our solar system, there may be creatures swimming through dark oceans, never knowing sunlight, never knowing us, living lives entirely separate. That is an astonishing thought. And it is a reminder of humility, that the universe is vaster, stranger, and more full of surprises than we ever imagined. So, as you lie here, in the gentle darkness of the room, think of the moons. Think of Earth's moon, silently orbiting in the night sky, having been there for billions of years and set to remain for billions more. Think of Europa, with its vast ocean beneath the ice, where life may be waiting to be discovered. Think of Enceladus, spraying water into space like a cosmic fountain, feeding Saturn's rings with its own breath. Think of Titan, with methane rain falling down, rivers flowing into seas, a world with weather and a liquid cycle like Earth's, but made of entirely different chemicals. Think of Io, burning with volcanic fire, pulled and squeezed by gravity until it can do nothing but erupt. Think of Triton, the captured wanderer, slowly moving toward its end, knowing its fate but having no way to change it. And let your thoughts drift like one of those moons, silently, gently, orbiting round and round, along an unchanging path, in the peace and quiet of space. Let the eyelids grow heavy. Let the mind relax completely. Sweet dreams of distant moons, of hidden oceans, of gravitational dances in the darkness. Until next time, in the next science story.